Talking about entropy in this video. So entropy, not to be confused with enthalpy, we want to make sure we pronunciate it well so it's not too confusing. And our symbol for entropy is a capital S. So enthalpy is H, right? That was our heat of reaction. Entropy is a capital S. And just like we did with enthalpy and energy, we're generally going to look at entropy coming in and out of our system. So we generally are going to look at our entropy change, delta S. What entropy is a measure of molecular disorder or randomness. So a measure of disorder or randomness. The more disordered, the more random something is, the higher its entropy. So it tells us how spread out, dispersed, chaotic that the system is. So something that's a gas, right? In a gas, I don't have any connections between particles. Each particle can go off and do its own thing independently of the next particle. It's spread out, it's kind of chaotic. Where a solid, where each particle is well connected to the neighboring particle, is more ordered. It has less entropy than something that's a gas. So a measure of disorder or randomness. And then again, for us, we're going to be looking at delta S mostly, so our entropy change. Again, always from the point of view of the system, unless we specify otherwise. So is my chemical system becoming more random or less random, right? More disordered or less disordered. So entropy change. And as always, it's going to be final minus initial. So if we have a negative value for our entropy change, right? If that's negative, that means my final entropy is less than my initial entropy, right? We could say that my entropy change is less than 1. If that's the case, right, I'm losing disorder, right? My system becomes less disordered or more ordered, if that makes more sense for you. So the system loses entropy, right? My final entropy is smaller than my initial, which is why it comes out to be negative. Our system becomes less disordered, or we could say more ordered. It's not standard to think about it that way because entropy is a measure of disorder, not order. So generally it's always in terms of disorder. Is it less disordered or more disordered? Sometimes I will say more ordered though. And then the opposite, if it's positive, if my entropy change is a positive value, right, it gained entropy, my final entropy is larger than my initial, right? Our entropy change is greater than 1 is a positive value. So our system gains entropy. My system becomes more disordered, less ordered. Oops, sorry about that, guys. That word just didn't quite fit there. We'll move it down. More disordered. Right? Less ordered. Again, entropy is a measure of disorder, not order. So that's why the ordered part I'm putting in parentheses. So some factors that affect entropy. We already talked about one of them, and that's the physical state. So as we go from a solid to a liquid to a gas, entropy's increasing, right? They're becoming more disordered. So kind of the one factor we're going to talk about, physical state. Right? A solid going to a liquid, going to a gas, right? In this direction, entropy is going to increase. Right? Becomes more disordered. We could draw an arrow in the opposite direction, right? We could say entropy decreases. Right? Becomes less disordered, becomes more ordered. Right? These guys, we should have reversible arrows on there, right? Gases can form liquids and liquids can form solids. When we do that, they're more ordered, they're less disordered. So there's a decrease in entropy. Right? Solids have lots of connections between particles. Right? Many bonds, intermolecular forces. It depends what type of solid it is as to what type of connection it is, but many connections between particles. Right? It has a definite shape, it has a definite volume, it's very well connected. Liquids, we have some connections, kind of in the middle, and then remember with gases, we have no connections between those particles. Right? Each one acts independently of each other, of the other. So each gas particle acts independently. If one wants to move left and the other wants to move right, that's fine. Solids, because of all those connections, the entire thing works together. So as we go from a solid to a liquid to a gas, it's becoming more disordered. As we go from a gas to a liquid to a solid, we're building those connections, it becomes more ordered. So physical states, one of the factors to consider when we're considering entropy changes. Another one has to do with the relative size. So relative size of our atoms. So in general, the bigger it is, we should say atoms, compounds, the larger it is, the bigger its entropy is going to be. So more bonds, greater entropy. So what happens is bonds aren't stationary. They do tend to vibrate, they stretch, they bend, they move. They create what are called microstates. The more microstates you have, the higher your entropy is going to be. So bonds stretch, bend, vibrate, etc. More bonds, more of this. Right? Creates what we call microstates. And all of this, right, more bonds, more bending, more stretching, more vibrating, all of this is going to increase my entropy. The more electrons you have, the larger your entropy. So relative size, not just of atoms, but compounds is kind of what I'm talking mostly about here, but more bonds, more atoms, greater entropy. Temperature is a really big one. Remember, temperature is a measure of our particles' average kinetic energy. Right? Temperature is not just how hot or cold something is, right? It's a measure of its average kinetic energy. It's generally related to molecular motion. If we have an increased energy, right, they have more kinetic energy. Remember, kinetic energy is energy in motion. So the more kinetic energy we have, the more motion we're going to have. So a measure of average, we should put average in there, that's actually important. Of the average kinetic energy of a substance. We generally say it's a measure of particle motion. A lot of times they'll say molecular motion, but it doesn't have to be a molecule. It could just be a particle, right? It could be an atom. So a measure of particle motion. So essentially, the higher the temperature, the more motion we have, the higher the entropy. So as temperature increases, entropy also increases. They're moving around more with more energy. That makes it more chaotic if we think about it in that term. So entropy usually increases for the following. Just kind of a quick summary for us. So entropy usually increases for the following. So melting, right? Going from a solid to a liquid, right? We're breaking connections between particles, becoming more random. Vaporization, breaking more connections, right? Going from a liquid to a gas. And then sublimation. Remember, sublimation is when we went from a solid all the way to a gas without going through the liquid state. So all of those involve breaking connections between particles, right? Making it more random. We could add decomposition reactions to this. Remember, in a decomposition reaction, we're going from one reactant to more than one product. So just by nature, the simple fact that we're going from one thing to more than one, that's more random. Instead of one neat, orderly, all well bonded to each other compound, we're going to separate things. So decomposition, we could do hydrogen peroxide decomposing to hydrogen plus oxygen, right? Something like that. We'd be breaking connections, right? Chemical bonds in this case. So decomposition is going to increase entropy. And then reactions that result in an increased number of gas moles. So reactions that result in an increased number of gas moles, or moles of gas, however you want to say it. I guess we could also add, or greater molar mass of the solid. Right? Remember, solids still have connections, but greater molar mass, more microstates. More microstates we have, the higher my entropy. So these things generally increase the entropy, right? They make it more disordered. More disordered. And then really the opposite of these, entropy usually decreases for the following. So again, if entropy is decreasing, it's becoming less disordered, right? More ordered. So for these ones, freezing, right? Going from a liquid to a solid, we're forming connections. Condensation, from a gas to a liquid, we're forming those connections. And then deposition. So freezing, condensation, deposition, combination reactions, right? It's more orderly once we combine them. We're going from more than one reactant to a single product. So we can just turn our arrow around on that last one. If I took hydrogen, let's actually make water this time. Let's do 2 hydrogen plus oxygen going to 2 water. And then precipitation reactions also. If you remember precipitation reactions from 150, 151, those were reactions where you had aqueous reactants and it produced an insoluble product, right? That insoluble product was my precipitate. It's solid, right? Because I'm going from things that are in solution. Solutions just by definition are random, right? Solutions are mixtures. Mixtures are random. So things that are in aqueous solution are always going to have a higher entropy than something that's just a pure state of matter. So the fact that we're forming a solid, something with lots of connections, something that's not just ions floating around in solution, it's becoming more ordered. So precipitation reactions are also going to have a decrease in entropy. So some examples for us. And I am stealing these examples right from the PowerPoint slides that I have posted. Sometimes I like to do different ones, so you get a couple examples, but I'm just stealing these directly from the slide. Sorry, guys. But we're going to determine, I'm going to give us some pairs. Determine which let's just say which in each pair has the highest or higher, greater, pick a word, Jen, entropy. And I'm gonna write down the examples, and then it would be really cool if you guys would pause the video and try to do it on your own and then come back and we'll go over the answers. So in our first example, we're gonna compare oxygen gas to oxygen liquid that is a thing at high pressure. C3H6 gas versus C4H10 gas. And again, so each of these sets of the two that I'm giving you, which one has the higher entropy is what I'm asking. C, let's do iron 3 nitrate. 3 I said. Actually, iron 2 nitrate, I copied it down wrong. And that is a solid versus iron solid. Helium versus neon. 2 more choices here for us. Carbon, which is solid at 25 degrees Celsius versus carbon solid at 35 degrees Celsius. And 1 mole of oxygen, that's in 2 liters, versus 1 mole of oxygen in 1 liter. I was getting ahead of myself. Okay, so again, if you would just pause the video real quick, go out and try to pick the answers on your own, and then restart the video and we will go through them. Okay, I'm gonna trust that you guys did that. So the first one, hopefully you guys picked the gas, right? That was our first, we said states of matter, right? So if something is solid, I have lots of connections between particles. If I have a liquid, I have some connections. If I have a gas, I have no connections. So given 2 identical compounds, one in a liquid state, one in a gaseous state, the gas is always going to be more random, so higher entropy for that one. C3H6 versus C4H10. This one, right? Bigger. This was our relative size example. I have more bonds, so I have more bending, stretching, vibrating, right? I have more microstates. So that is going to be my more random one. Iron 2 nitrate versus iron. We're gonna pick this one. And again, it's bigger. We had said larger molar mass for our solids. So more microstates again. Kind of the same answer for this one, it's bigger. So neon is a larger atom, I have more electrons, larger molar mass. E, yeah, higher temperature, good. Right, the higher the temperature, the more molecular motion, in this case we should just say particle motion it has, right? They're traveling with more kinetic energy. Remember, unless we're at absolute zero, they're constantly moving. This one's just moving with more energy, so more random, more chaotic, more dispersed. And speaking of dispersed, if I have 1 mole in 2 liters versus 1 mole in 1 liter, it's going to be more spread out, more random. So an increase in entropy for that one compared to 1 mole in 1 liter. I wanted to just a couple quick examples with some reactions, so just a few more, predicting whether entropy is increasing or decreasing. So in this one, I have 2 sulfur dioxides, which are gas, and reacting it with an oxygen gas, and we're going to 2 sulfur trioxide gases. So this is one of the ones where we're going to just look at moles of gas. So on my reactant side, I have 3 moles of gas, right? 2 sulfur dioxide and 1 oxygen. So 3 moles of gas. And then on my product side, I only have 2 moles of gas. So because my moles of gas are decreasing, not increasing, this is actually going to be a decrease in entropy, right? It's becoming more ordered. You can even look at this one. If you didn't look at the gas, you could look at it as a combination reaction, right? If we go back up, we had that combination reactions were a decrease in entropy. So for this reaction, I would actually expect my entropy change to be negative, right? It's a decrease in entropy, right? A decrease in disorder. So I'm going to have a negative value for my entropy change for this reaction. Let's actually add combination reaction. That might be the easier way to look at this one. We could do 2 ozone gases going to 3 oxygen gases. This one I would just do straight moles of gas. I'm going from 2 moles of gas to 3 moles of gas. Right, so this one I'm actually going to have an increase in entropy. So if we were to look at our sign on our entropy change, it's going to be positive, right? In the end, I have more entropy than I started. So finest minus initial is going to be a positive value. Another one for us, to have calcium carbonate, which is solid, and then that's reacting with 2 hydrochloric acid, so aqueous, 2 of them, and we're forming calcium chloride, which is aqueous, plus water liquid, plus carbon dioxide gas. So increase or decrease in entropy on this one. Yeah, this one's going to have an increase. Hopefully that's what you guys are thinking. So my final entropy, right? I'm gaining disorder. So my final is greater than my initial, so a positive change. And you can look at this one a few ways too. I have a solid, so that's nice and ordered. Over here I don't have any solid. Here I have 1 mole of gas. On that side I don't have any. Anytime you're forming, breaking connections, that sort of thing, entropy is going to be increasing. So increase in entropy for that one.